Hello and welcome again to the 6th video on the normal distribution for Year 13 Edexcel Pearson A-Level. So we've done the groundwork. Now the last bits of the Chapter 3 do get quite tricky, but again, like anything, with enough hard practice it will be resolved in terms of you finding it much easier and understanding the content. But just a pre-warning, it does get fairly hard going fairly soon. So the best way of doing these is to have lots and lots of practice, which I'm going to prescribe to you at the end of this video. So before we do that though, we do need to get a few warm-up questions sorted out, so here they are. So 4 to try today. As ever, try these independently and only press play when you're ready to see the solutions to them, and hopefully you'll find that you've got these cracked. So without further ado, let's have a look at the solutions, starting of course with question number 1. So question 1, we've got a company that's collected data about how many kilometres, D, employees travelled to work each day. The results are shown in the below table. So it says use linear interpolation to estimate the median distance travelled. So for part A, we need to work out what the total frequency is, because the median is going to be halfway along. So if we total up all these frequencies, we've got 1, we've got 9, 19, 14 and 7, you should find, if you add all those up together, you get a grand total of 50. So therefore, the median, Q2, because it's continuous, we can just half this number. 50 divided by 2 is 25, so the median isn't 25, but it is the 25th value. At this stage, what I'd often suggest is to do a cumulative frequency of the running total. So obviously before we begin, that's got a frequency of 0. Up to that point we've got a frequency of 1. 1 plus 9 is 10. 10 plus 19, 29. 29 plus 14 gives us 43. And then 43 plus 7 gives 50. So the 25th value is going to be in between the 10th and the 29th, so the 25th value is going to be somewhere in this interval. So now to use interpolation, we start where this interval starts. So this interval starts at 10. Now let's be thinking, how far into this interval is the 25th value? Well, this interval starts after the 10th value. The 25th is 15 values after it. And so the median will be the 15th value out of 19. It'll be the 15th out of 19 in this interval. So it'll be this fraction through the interval. So we start where the interval starts, but we're going to add in this fraction of, multiply, the width of the interval, which is 5. And that'll give us an estimate of what our median should be. So we just perform this calculation for A, and we've got our estimate. So we're going to have 10 plus 15 over 19 multiplied by 5, and that gives us 3 significant figures, if we like, which should be absolutely fine, about 13.9 kilometres. And for part B, we're asked to estimate the mean and standard deviation of the distances. Now this here is a class whiz job. So I'm just going to put here, just for the examiner's use if you wanted to, using the class whiz or using the calculator you could say. What we do need for grouped data is the midpoints. So if we work out the midpoints here first, halfway between 0 and 5 is 2.5. Halfway between 5 and 10, 7.5. Next midpoint is 12.5. Between 15 and 25 is 20. And this final midpoint here is 32.5. So how do we use the calculator to compute this? Well, first of all, get the calculator on, press on, normally a good start. Then we go menu and press option 6. This is only one variable, the only variable being the distances to work, so we press option 1. Now we just type in where it says x, we're going to put the midpoints, frequencies, self-explanatory. So 2.5, then 7.5. The next one is 12.5, and 20, and then finally 32.5. Then moving along and doing the frequencies, 1, 9, 19, 14, and 7. So press equals, and once all the data's in, we now press OPTN and go to one variable calculation. So press option 3, and now we can see the estimates for the mean and standard deviation. So the estimated mean, x bar, is 16.3. So the mean distance is 16.3 kilometers. And the standard deviation of those distances, this subscript D is optional. We just go back here and look where it says sigma x. So sigma x gives us 7.9923 significant figures. 7.99 kilometers is the standard deviation of distances. So that's how we'd use the calculator if we had no summary data. Let's have a look at question 2. Question 2, you will find these numbers very, very similar indeed, to say the least, to question 1. So I'm going to explain why afterwards. It's to get you to see there's more than one way of being asked the same question, essentially. So the same company from 1 is also recording how long it takes employees to complete an online training module. Although instead of having a table this time, we've got the results, T minutes, which have been recorded for 50 sampled employees and then have been coded in terms of X. So T has been coded into X. The summary statistics for X are as follows. So the sum of Fx is 815, and the sum of F times X squared is 16,475. For part A, we have to calculate the mean and standard deviation of these coded times. Now, if we've got coded data, this is where we need to know how to use the formula for calculating standard deviation when we have these summary statistics. And the formula is as follows. Okay, this is a formula we need to be using. So, the next step, and it is just a case of substituting in what we know into this formula. So to calculate the standard deviation, we need the mean first of all. So the mean is this thing here. So the mean, by the way, you are given a version of this formula in the formula book, only the version you're given doesn't include the F's. So the version you're given is for without a grouped frequency table. But it can be altered for the formula for the standard deviation for a grouped frequency table by just inserting an F in before each instance of X squared and of X. So if you have a formula booklet in front of you, you can probably see what I mean. Anyway, the mean of X is the sum of F of X divided by the sum of all the values you've added. So we know what F of X is. It's 815. And there's 50 sample employees, so 815 divided by 50. So what does that give us? Get back into normal mode. Oops. Pick 0 of that. So 815 divided by 50. That gives us a mean of 16.3 kilometers. And the standard deviation, we just plug in the values into this formula because this will give us sigma. So sigma is going to be the sum of fx squared, so 16,475, all divided by n, which is 50, minus this thing here, which is the mean, all squared. So we're going to minus off 16.3 squared because this here is the mean, which we just worked out earlier. And all of that, of course, don't forget to square root the thing. So if we now do that, so we've got the square root of 16,475 over 50, subtract 16.3 squared, and the standard deviation is 7.99. Whoops, I've put kilometres there, I don't mean kilometres, so let's put 16.3, and here 7.99. So you should notice from question 1 these figures are exactly the same, and that's because it is exactly the same data, essentially, just presented in 2 different ways. So just to show you how the same question can be presented in one way, for example in a group frequency table, but you also need to know how to calculate statistics if you're given these summary statistics as follows. So you need to know how to do both. So that's the mean and standard deviation of the coded times. However, because these are coded, for part B, we need to work out the data for the actual times. So what's the actual mean time taken and the standard deviation of the times? So for part B, to find the mean time, we essentially just make t the subject of this equation. So we multiply both sides by 2, which gives us 2x, but because we're talking about the mean, that's 2 lots of the mean of the coded times, and then we'd add 20. So that's going to be 2 times 16.3 plus 20, and if we try that, you should find you get 52.6 minutes. So almost an hour to complete the training. And you need to recall the standard deviation is not affected by a shift in the data. So if we just take away 20 from all the times, that won't affect the spread. The only thing that will affect the spread is this factor of 2 here. So we've divided by 2. So therefore, the standard deviation of the actual times, we need to undo the dividing by 2 and multiply by 2. So that's going to be 2 lots of the standard deviation of the coded times. So it's going to be 2 lots of 7.99. And so that's going to give us approximately 15.98 minutes. If you want to, you could have just called that 16.0. To 3 different figures, it's 16.0. In fact, we'll do that for consistency. I'll just call it 16.0. So I've got it to the same number of significant figures. For question number 3 of the warm-up, we've got this discrete random variable big X with the following probability distribution. So X could be either A, B or C, and the probability of the distribution taking any one of these particular values is as follows. It's log base 64 of A, for it to be actually being A. The chance of it being B is log base 64 of B. The chance of the distribution taking the value C is log base 64 of C. Where A, B and C are all distinct integers, in other words different integers, all whole numbers, the probabilities are all greater than 0. Show you're working clearly, find the values of A, B and C. Well, going back to GCSE even, we should know that the sum of all the probabilities of any one event will total up to exactly 1. So if we sum up all these probabilities of X equaling X, we'll get 1. So in other words, log base 64 of A plus log base 64 of B plus log base 64 of C will equal 1. We now need to use laws of logs. So log of one thing plus log of the other plus log of the other. Because these logs are all to the same base, we can combine this as a product. So this is the same as log base 64 of A multiplied by B multiplied by C. So log 64 ABC equals 1. So therefore, we can work out what ABC is. So ABC is going to be simply 64, because the log of any number, if the base is the same as a number, it's always going to be 1. As a double check, so that's going to be 64, I mean to say. So ABC needs to be 64, because the log of base 64 of 64 itself is 1. And now we need to sort of puzzle this out. So A, B and C are all different whole numbers. So could A be 1, for example? So could it be like 1 times 2 times 32? Well, it can't, because if you do the log of 1 to any base, that comes out to be 0. So if I show you here, log base 64 of 1 equals 0. But we're told here, clearly, that all of them are greater than 0. And so A, B, C can't be equal to 1, because that would give probabilities of being 0. So could A be 2? In fact, A could indeed be 2. It would turn out by trial and error or otherwise, just by exhaustion, that therefore A would have to be 2, B would have to be 4, and C would have to be 8. That's the only combination of 3 different integers where if we multiply them all together, we get 2 times 4 times 8 is 64, whereby none of them are equal to 1. Because if A, B or C was equal to 1, we'd get a probability of 0, which is not allowed. So a very similar question to what came up in an exam previously. That's how you'd tackle that one. And finally, warm-up 4. So we have a machine putting liquid into bottles of medicine. The amount of liquid in each bottle, D milliliters, follows a normal distribution with mean of 28 milliliters. So we can already just put this into the standard notation. So D is going to be normal with a mean of 28. We don't know the standard deviation or variance, so we'll just leave this as sigma squared, because you don't know it yet. Although we do know that 5% of the bottles contain less than 27.29 mil. So we need to find to 2 decimal places the value of some number k, such that the probability that the amount of medicine is in between 27.29 mil and k mils is 0.55. So at this stage, I think it's probably wise to just sketch out what we know already. So we know it's normal, so we can draw the normal curve on. We know the mean, so we can put the mean of 28 on here. And we're also told that 5% of bottles contain less than 27.29. So if I draw this on here, 27.29 goes there, and this proportion of the curve, where it's 27.29 mils or less, is 5%, which is 0.05. So that's our starting point. The thing here is, if you don't know the mean, the standard deviation, or neither, it's almost always a good idea to code this into the standard normal distribution. So that's what we've known and used. So we can now standardize this, not with a straight line. So what I had originally over here was a distribution of D. This is D, which is normal, 28, and sigma squared. Whereas if I standardize this, if I just borrow my own work and pop it over here for a moment, just saves time, then what's going to happen is the mean of the standard norm distribution is of course 0, which we need to know and remember. The standard norm distribution has a mean of 0, standard deviation, and variance of 1, so that's 1 squared. So to code it, I take each value upon the curve, in this case 27.29, I subtract the mean, which I know is 28, and divide by the standard deviation, like so. And so we can now use the inverse normal in a moment. So I can say here that the probability of the normal, standard normal curve being less than 27.29 minus 28 over sigma, I require that to be 0.05. So if I use the inverse normal to get the appropriate value, the z value as it were, menu 7 inverse normal, I want the required area to be 0.05. The standard deviation is 1 for the standard normal and the mean is 0, so I can leave these as they are. Press equals. That tells me that this value here needs to be minus 1.6448 to give that required probability of 0.05. So therefore, this here must be minus 1.644-ish. I'll just leave it here with a few dots on in a moment to just denote that this isn't exact, nor do I want to round it. Although what I can do here is rearrange. So if I multiply both sides by sigma, I can work out what 27.29 minus 28 is as well. So 27.29 subtract 28, that gives minus 0.71. So minus 0.71 equals minus 1.6448, 5-ish sigma. Therefore, if I divide both sides by minus 1.644856, I can work out what sigma is. So sigma is going to be minus 0.71 divided by minus 1.64485, and that's going to give us about 0.43165. So now we can work out what this value of k is. So I'm wanting the proportion of the curve in between 27.29 and k to be 0.55. So I'm wanting up to k, if I put k here, I want the bit in the middle, middle-ish, to be 0.55. However, we can now use the bit on the left as well, that's 0.05. This needs to be 0.55, like the question says. So therefore, I want the probability that d is less than k to be this 0.55 plus this 0.5. I want it to be 0.6. I can now return to the original distribution of d because I've worked out the standard deviation of d now. Standard deviation of d is 0.43165. So what we can do here is just find this proportion directly on the calculator. So if we go now to menu, option 7, and go to normal CD, then I can work out this required proportion, which needs to be 60% of the curve, k, and to the left. So the lower bound is unlimited, it's as low as we can go. I'll put in minus 999,999. The upper bound is k, which is what we want to work out. In fact, what we do need to do here, I apologise, we need the inverse normal. I'm being very, very silly. Sorry, menu 7, inverse normal, silly me. I need the area to be 0.6. I know now the standard deviation sigma is 0.43165, and the mean, of course, was 28. So we press this in, and again, and this will give us the required value, which will be k, which will give this required proportion of the curve 0.6. So press equals, I get here that k must be 28.11 milliliters. So we can now have a look at the main bit of today's lesson, which is approximating a binomial distribution. So in certain circumstances, we can use the normal distribution to approximate the binomial. So we need two things to do this. We need, first of all, n to be large and the proportion to be close to 0.5. If those two things hold, the binomial distribution B and P can be approximated by the normal distribution n mu sigma squared, where the mean is n times p and the standard deviation is the square root of n times p multiplied by 1 minus p. So n needing to be large sounds vague because the exact criteria of what determines if n is large enough, as it were, is fairly complex and well beyond the scope of the A-level course. However, typically, the following will be true if n is sufficiently large. So first of all, n times p, the mean, will typically be bigger than 10, and also n times p minus 1 will also be greater than 10. But importantly, and in general, n will be at least 50, generally speaking. When n is at least 50 in questions, that tends to be when the binomial, the normal approximation to a binomial comes up. Let's have a look at a worked example now. So generating a normal approximation to a binomial. We have a biased coin which is tossed, and the probability of heads is about 53%, so it's slightly biased towards heads. It's tossed 100 times, number of heads is recorded. So first of all, it says write down a binomial model for x. So for part A, just say x is binomial, 100 flips, probability of landing on heads, 0.53. So y can x be approximated with a normal distribution? So for approximation, I'm going to call big Y. Big X is the exact binomial. Well, those two reasons from before still hold. So the number of trials is large. N is 100, that's 50 or more. And the probability of getting heads is 0.53, which is close to 0.5. So those two things need to be said, and then we're okay. Now for part C, it says here, find the values of mu and sigma. So for C, the original exact binomial is 100 and 0.53. Therefore y, I mean to say that the original is binomial. Y is therefore going to be normal, the approximation to that. Now n times p is 100 times 0.53, and sigma squared is going to be 100 times 0.53 times 1 minus 0.53. So 100 times 0.53 is going to give us 53. And this here, 100 times 0.53 times 1 minus 0.53. One minus 0.53 is 0.47. That tells us that the variance, not the standard deviation, but the variance is 24.91. So in other words, the standard deviation is the square root of 24.91. So if we want to work out mu and sigma, then mu is 53, like we can see, and sigma is a square root of 24.91, so root 24.91, That gives us 4.99. Whoops. So that's all we need to do for that one. Next, if we are going to approximate the binomial using a normal distribution, we need to consider the fact that the binomial distribution is obviously different to the normal. One is continuous, but the binomial distribution is for discrete data. So what we need to do is apply something called a continuity correction to the distribution. So what is a continuity correction? Well, like I've just said, the binomial distribution is discrete, whereas the normal is continuous. So therefore, if you're using a normal approximation to a binomial, we need to apply continuity correction when calculating probabilities. That's because we can, for example, work out the binomial distribution, the probability of x being 2, x being 3, whereas if it's a normal distribution, x being equal to 2 or 3 has a probability of 0, because a continuous distribution can never have exactly a particular value. It's either going to be infinitesimally below or above. So I'm going to show you what it looks like with reference to a couple of diagrams or so. So the diagrams below are going to be showing big X, which is modelled by binomial, 14 trials, 0.5 probability of success, which can be approximated by the normal, which we're going to call big Y, with the expected mean n times p, 14 times 0.5 is 7, then 14 times 0.5 times 0.5, again all square rooted, gives 1.87 for the standard deviation. Therefore the variance is 1.87 squared. So this here shows the distribution. So these bars are the binomial bars. So let's see, for example, we wanted to approximate the probability of the binomial distribution taking a value of 5 or greater. 5 or greater means 6, 7, 8 and so on, highlighted in the blue. But because the normal distribution is for continuous data, we need to approximate the exact value of 5 by taking half a unit either side. So the unitary value of 5 on the normal we'd take in being in between 4.5 and 5.5. Therefore, using the normal approximation, 5 or more for the discrete value we'd interpret as the continuous having to be 5.5 or more, because we'd take the 6 in the approximation to be between 5.5 and 6.5. Another example, let's imagine we wanted to approximate the probability of a binomial distribution equaling 9 using the normal. Well, 9 we take as in being in between 8.5 and 9.5 using the normal distribution. So we'd approximate this by working out the area under the curve for the normal distribution in between the points 8.5 and 9.5. Finally, a third diagram, if we wanted to work out the approximation for the binomial being 3 or less, we'd approximate this as seeing when the normal is 3.5 or less, because 3 or less is 0, 1, 2 or 3, but of course using the normal approximation we take the unit 3 as being in between 2.5 and 3.5 for the boundaries. Let's try a couple of worked examples using this idea of the continuity correction. So, the binomial random variable, big X, follows the binomial with a number of trials 150, probability of success 0.48, and we're going to approximate this with the normal random variable y, np 72, and n times p times 1 minus p, 6.12 squared. Use this approximation to find the probability that x is less than 70 first of all. So for A, the probability that big X is less than 70, that's approximated by the probability of big Y being less than or equal to 70.5. So then we use the calculator for the normal distribution. So again, we press menu, then we go to option 7, we now go for normal CD, and we type in the limits as needed. So the upper limit is 70.5, the lower is unbounded, so just type in a really negative number for the lower, say minus 999,999. Now the standard deviation for this one is 6.12, the variance is 6.12 squared, but the standard deviation is 6.12, and of course the mean is 72. So press equals and equals again, and then we see that this approximates to a probability of approximately 0.4032. And for part B, we want an approximation to the binomial probability of x being in between 80 and less than 90. So 80 and upwards, but less than 90. So we say this is approximately the same as a probability of big Y, the normal approximation, as being as little as 79.5, because 80 spans from 79.5 to 80.5. But because at the higher end we're not wanting to include 90, we need to cut off before 90. The 90 point is between 89.5 and 90.5. So what we want here is we want it to be less than 89.5. So again, just use the calculator for that. And what we'd find here is as follows. So press AC. This time the lower bound 79.5, the upper bound 89.5. Now because it's continuous, this symbol here is the same as that, so it doesn't really matter. These are interchangeable on a continuous. So 79.5 up to 89.5. Here the parameters for the standard deviation and mean are unchanged, so press equals to C. We get a approximation of the probability of 0.1081. So let's have a look at another example. So normal approximation to binomial, once again. This time we're talking about flower bulbs. So this worked example is a bit more sort of exam style. So for a particular type of flower bulb, 52% will produce yellow flowers, and a random sample of 120 bulbs is planted. We are asked to calculate the percentage error incurred when using a normal approximation to estimate the probability that there are exactly 70 yellow flowers. Well, first of all, the actual distribution without the approximation would be binomial. We're either going to produce a yellow flower or not. So the actual distribution x would be binomial, and we'd have 120 flowers in total, 120 bulbs rather, with probability of it turning yellow 0.52. So this can be approximated by the normal, if I make the normal big Y. So the expected mean is 120 times 0.52. And the variance will be 120 times 0.52 times 0.48. In other words, 1 minus 0.52. And this figure here will tell us the variance. So in other words, we could approximate it by the normal. So what's 120 multiplied by 0.52? Well, 120 multiplied by 0.52 gives us 62.4, and 120 times 0.52 times 0.48, I can just take this figure here, multiply by another 0.48, and I get 29.952. So in other words, the standard deviation is going to be the square root of 29.952. So next, what we need to do is to consider how we're going to use this normal approximation to answer this particular question. If we wanted to use the exact binomial and we wanted to estimate, actually arrive at the probability that there are exactly yellow flowers, 70 yellow flowers, then the exact probability of having exactly 70 yellow flowers we can do using the binomial function on the calculator. So for this one, we'd go to Menu, Option 7. We then go to Binomial PD, because we want to work out the exact probability of 70. So we want 70 out of 120 flowers that turn yellow. And the probability of just one flower turning yellow, of course, is 0.52, like we said. So press equals and equals again. That gives us a probability of 0.027939. So 0.027939. And the normal approximation of it being 70 flowers, we can approximate by taking the limits 69.5 up to 70.5 by using the continuity correction. So now we need to change from the binomial to the normal, because y is the normal approximation. So again, using the calculator, I'll just move this to the side so we can see what we're doing. We go Menu, Option 7. Now we go for the normal CD function, so Option 2. So the lower bound is 69.5. The upper bound is 70.5. This time, the standard deviation is a square root of 29.952. And the mean is 62.4, which is almost hidden there. So 62.4, press equals and equals again, and we get 0.027829. So I'll round that to 0.027830 to 5 significant figures. 0.027830. I'll just double check I remember those numbers correctly. So yes, I have. So therefore, we need to work out the percentage error. So for percentage error, is going to be the error divided by the actual multiplied by 100. So the actual error is going to be 0.0, the difference between the real and the approximate, 0.027939 minus 0.027830. So we're going to take that, we're going to divide that whole thing by the actual. So the exact, without approximating with a normal, the exact is 0.027939. Then multiply that fraction by 100 to change it into a percentage error rather than a fractional error. 67939 and times 100. So if we just plug this in, press equals and hope, then we've got it. So go back into normal mode. So 0.027939 subtract 0.027830, take all of that and divide by the actual 0.027939 times by 100, press equals. We get a percentage error of about 0.390, so less than a 1% error with that calculation. So as you can see, the normal approximation does fit very well to the exact probability. So a 0.390% error, which is Very accurate indeed. Next, we're going to move onwards and upwards. So here's a first of two exam-style examples for you to get your head around. So we're told here that for a particular type of bulb, a plant bulb this is, 36% of them grow into plants with blue flowers, and the rest of them grow into plants with white flowers. So it's either blue or white. So already this is a massive clue, it's going to be a binomial job. So bulbs are sold in mixed bags of 40. So we know how many bags there are, we know it's only two outcomes, so it's definitely going to be binomial. Russell selects a random sample of 5 bags of these 40 bulbs. Find the probability that fewer than 2 of these bags will contain more bulbs that grow into plants with blue flowers than grow into plants with white flowers. Well, before we talk about multiple bags, we just need to start thinking about just one bag of 40. So for 40 bulbs in total, what would the distribution be of expected number of bulbs that flower into blue flowered plants? So for just one bag of 40, for 40 bulbs, let P be the distribution of the number of blue flowered plants out of 40. Then big P will be binomial distributed, 40 plants in total. The proportion of blue flowered plants should be 0.36. For part A, we're interested in the proportion of bags which have more than white flowers. So we want the probability of bulbs growing into blue flowers. We want more blue than white. So we want at least half of these 40 to be blue. So for one bag, we're interested in the proportion of these plants. We want the probability that P, number of plants that turn blue, is at least half. Well, we want actually more blue. So we want more than half. So we want at least 21. If it was 20, it'd be exactly half. We're wanting more than half. So we want at least 21 to be blue. So that is the same as us asking for all of them, apart from those bags which have 20 or fewer blue in. So this is where we need to use the calculator. So we need to get the binomial up and running. So we go menu, option 7, we scroll down, go to binomial CD, press variable, and what we're wanting here is to work out what's the probability of 20 or less out of 40 flowering into blue flowered plants. The proportion of those with blue flowers is 0.36, so we type 0.36 in, and we get 0.97596 and so on. So we need to do 1 minus this 0.97599. So if we do this, we'll get our probability for just one bag having more than half blue flowers in it. So if I go back to normal mode, menu 1, that probability is stored. I do 1 subtract that. And because this isn't our final answer, I'm not going to round too soon. I'm going to leave this with more significant figures on than I normally would. 0.024. I'm going to give this 0.024 0038. 0.024 0038. So about 2.5% chance that one bag has bulbs where more than half turn blue. So we've now worked out the relevant probability for just one bag. We can now scale up and think about these 5 bags in total. So whereas here we were talking about the distribution of number of bulbs out of 40, now we need to talk about distribution of number of bags in which more than half of those bags end up with blue flowers in them. More than half of the 40 bulbs in these bags, I should say, have blue flowers. So now let's introduce a new variable, B for bags. Not very imaginative, but there you go. So now I'm just going to say, let B be the number of bags out of 5 with more than 50% Let's move this out of the way slightly. Yes, I need a distribution of number of bags out of 5 with more than 50% blue flowered plants. So the number of bags will be binomial distributed, 5 bags in total. The chance of just one bag having more than half blue flowers is 0.0240038. So I want the probability that fewer than 2 have more than half blue flowers. So I want the probability fewer than 2. So what's the chance that less than 2 bags end up with more than 50% of those bulbs flowering blue? Well, if I want fewer than 2 bags, that's the same as the probability of having up to and including only 1 bag with at least half, sorry, more than half being blue. So now I use again the calculator and change the parameters. So menu 7 normal, sorry, binomial CD. Press option 2 for variable. Now I've got 5 bags. I want to work out the probability that 1 or fewer, up to 1, of those 5 bags has more than half blue flowering bulbs in it. That probability from before, we can press ANS to get that back. It was about 0.024. The calculator's rounding it here, but it will actually know this is a number which doesn't just stop at 0.024. So the calculator will take into the extra accuracy from that. So if I press equals, that will generate the required probability, which we can see is 0.9945. And that's part A. Part B is introduced by saying, using a normal approximation, the probability of more than 244 of these N bulbs growing into blue flowers is 0.0521 to 4 decimal places. It's now asking us to find the value of N, which will satisfy that relation. So what we need to think about now is how to approximate this as a normal distribution. So first of all, I'm going to let big X be the original and exact binomial distribution of blue flowered bulbs out of these 244. I'm going to let big Y be the normal approximation of that normal distribution of blue flowered bulbs out of 244. Then we can set it up as follows. So the original actual true binomial is 244 0.36, and that is approximated by the normal, which is NP 1 minus P. So we've got N here, which we don't know what it is. So this Y, if I fill in what I do know, we don't know what N is, but I do know the proportion of these blue flowering plants is 0.36. So NP is 0.36N. And N times P times 1 minus P, again not knowing what N is, but I do know that P is 0.36, and so therefore 1 minus P will be 0.64. So if we do this next, so 0.36 times 0.64, I get 0.2304. So that's going to be 0.2304N. So from this, that's the variance, so therefore the standard deviation, sigma, is going to be the square root of that. So sigma is going to be that number square rooted root n. So what's the square root of 0.2304? I'll just square root that answer. I get 0.48. So sigma is the square root of 0.2304n, which is 0.48 root n. So now I can think about what this distribution looks like. I want to find the value of n. Let's use this information that we're given here. So this information, the probability that 244, more than 244, of these n bulbs that will grow into blue flowers is 0.0521. So if I get the pen going and just sketch this out, which is normally a good idea, I think. The normal approximation will obviously look like a normal curve. The mean, which is NP, so the mean is 0.36n. So this is the mean. This is the variance. That's the standard deviation. So I'm wanting to find the proportion of more than 244 bulbs growing into blue flowers. Now we need to remember the continuity correction. More than 244 means I'm wanting to find the point where it's more than 244.5. So I'm wanting this region on the right-hand side of 244.5. And we're told in the question that this proportion is 0.0521. So in fact, this proportion here is 0.0521. So I can change the colour of that to the yellow. But because we don't know the actual exact standard deviation, I know in terms of n, we need to standardise this curve. So that's 0.0521. We now need to standardise this normal approximation y. So if we take all of this and standardise it, which is what we need to do, we need to just remember how to standardise a normal. So we subtract from all points the mean, and then we divide by the standard deviation. So it's going to look like this next. Same curve, same characteristic curve anyway. The mean will then transform to 0, of course, and this point here, 244.5, I subtract the mean from that, so this is going to be 244.5 minus 0.36n divided by the standard deviation, which is 0.48 root n. And again, this proportion of the curve is still 0.0521. So now we can set up the problem and solve. So, just recall what we're told. So, if this bit here is 0.0521, then this region here on the other side of the curve is going to be 1 subtract 0.0521. And of course we need to remember now we're talking about the standard normal distribution. This here is Z, mean 0, standard deviation of 1. So, using this, the probability of being over on this side here, of Z being less than this value, 244.5 minus 0.36n, all over 0.48 root n, is 1 minus 0.0521, which gives us 0.9479. So to get this z value for what would give this probability, we use the inverse normal function now. So therefore we can say, using the inverse function, we can work out what the value of 244.5 minus 0.36n all over 0.48 root n would be. So recalling how to do this, it's menu, it's option 7, we're going to go for inverse normal, option 3. So our required area of this curve is 0.9479, and it is the standardized normal which we got it into. So we leave sigma as 1 and mu as 0, press equals and equals again. We require this value here to be 1.6248. So I'm going to give this in its full number here, so we don't have any rounding error. So I need that to be 1.62482438. We now can rearrange this and eventually solve it. This looks like something quite horrible to solve, but eventually you will see, hopefully it looks quite familiar once you unravel it. So what we can do here is multiply both sides by 0.48 root n. So if I multiply this by 0.48 root n, and the other side by 0.48 root n, then I get 244.5 minus 0.36n equals this number here multiplied by 0.48 root n. So I take this value, which will be stored if I go back to the normal mode. So times that by 0.48, I get this 0.779916 business. So 0.779916, or 99156. Horrible numbers. 869. We can now rearrange this into a standard form, set it all equal to 0 on one side of the equation. So if I add 0.36n to both sides and subtract if I subtract 244.5, so I'm going to plus 0.36n and minus 244.5 from one side, and do the same over here. I'll then get that 0 equals 0.36n plus 0.779916 root n minus 244.5. This goes back now to year 12. So all links together even now. So you could hopefully spot here with a bit of intuition and care that this is actually a hidden quadratic. This is a hidden quadratic in terms of root n. So we can solve this quadratic now in terms of root n. Because here, this is root n, this is normal n. So this is power 1, that's power a half. If you remember what I've told you before, if one power is double the other, that's a good clue that we're talking about a hidden quadratic. This line isn't straight, which is bugging me. It might be bugging you. Still not straight. There we go. So we can now use a calculator to solve this hidden quadratic. So we go Menu, I'm going to store this here. That's a useful thing to have stored, this value. Menu, option A. I want to solve a polynomial. Degree 2 means I'm solving a quadratic, in this case a hidden quadratic, but a quadratic all the same. So the x squared term relates to the n coefficient. That's 0.36. This number here is that previous answer I stored, so press ANS. And this figure here is minus 244.5. So minus 244.5, press equals and then equals again. One value of n is 25, sounds possible. Another value is minus 27. So we can't really have here, remember this here, working out root n, we can't have the square root of something where it's a negative. So we've got to say that therefore the value we're after is this, which is almost exactly 25. So therefore the quadratic in root n must be 25. So therefore n itself must be 25 squared, which is 625. So without scaring you too much, I'm hoping to show you that these questions can be pretty nasty. The only way to get good at them is to practice them, and to practice lots of them at that. So that's one actual exam question which came up. Let's have a look at another one, and then after the second one, it's over to you to try some of these on your own. Lastly, a second exam-style worked example. So this time we've got a company that sells and claims that 55% of its seeds germinate. So write down a reason why the company should not just try their claim by testing every single seed they produce. So this is a fairly obvious, I'm hoping, one marker. So essentially if they tested every single seed, and it's a company, companies have to make money. If they tested every single seed, there'd be none left to sell. So the first thing is we just need to say something like this. If all seeds are tested, then none can be sold. So that's why you shouldn't really do it. I mean, they could, but it wouldn't be exactly the best business model. So something along those lines for Part A would do. Part B, it says, assuming that the company's claim is correct, calculate the probability that in at least half the trays, 15 or more of the seeds will germinate. So here we're actually talking about two different things. The first thing is just for one tray. So if you just think about it just for one tray, each tray has got 24 seeds in it. Each seed will either germinate or not, so this is going to be a binomial question. A seed germinates or not. We know how many seeds there are, with only two outcomes. So the first thing to say here is we can let S for seeds, be the distribution of germinating seeds out of 24. So the number of seeds you can expect to germinate out of 24 will be binomially distributed, 24 seeds, 0.55 proportion of any one seed germinating. So for this one, we can calculate the probability that 15 or more germinate for just one tray of 24. So the probability of having 15 or more germinating seeds, so used to using big X, S being the number of seeds, 15 or more germinating seeds, that's 1 minus a probability that actually 14 or fewer germinate. So we can work this out now using the calculation on the class whiz. So if we just type in now, menu option 7 for distribution, so menu 7, we want the binomial CD, which is scrolling down and pressing option 1, press 2 for variable. Now here we're wanting 14 or fewer. So 14 or fewer out of a total number of 24, whether proportion of a germinating seed or not is 0.55. So press equals and equals again. That gives us 0.70087 and so on and so on. 0.70087. This isn't our final answer, so that's why I'm just doing a ... thing over here, to just denote that actually this isn't something I'm going to round yet. Pardon me. So now what we can do is do 1 minus that, because here I've just worked out the probability of having 14 or fewer which are germinating, which is this. We want obviously 15 or greater, hence is why we're doing 1 minus that. So now we can go to the calculator, press menu 1, that previous answer will be stored like so, so 1 minus our previous answer will give us 0.299. Now give this to a few more decimal places, because this isn't our final answer we need, so don't incur any rounding error, just either store that somewhere, write it in your margin in the exam, 0.299127 I'm going to call that. Going to give it to 6 dp, 0.299127. So that's the chance for just one box of having 15 or more germinating. But for part B, the question is asking us that across multiple trays, across 10 trays, what's the chance of having at least half of these trays having 15 or more germinating seeds. So now it's like a nested binomial question. It's another binomial question within a binomial. So now we need to think about the distribution of number of trays with 15 or more germinating seeds. And we can use this probability here to help us. So across the 10 trays, we can take this probability here, this 0.299127, that's the probability of just one tray having 15 or more germinating seeds. So if we're wanting to work out at least half of the trays having 15 or more germinating seeds, well, half of 10 trays is going to be 5 trays. So if we let T, big T, be the number of trays out of 10 where 15 or more seeds germinate, the number of trays expected with 15 or more germinating seeds will again be binomially distributed, because either a tray has 15 or more germinating seeds or it does not. Binomially distributed, 10 trays in total. The probability of just one tray having 15 or more germinating seeds is 0.299127, which is what we calculated for the first part of part B. So we're using this here over there. So we want at least half of these trays with 15 or more germinating seeds. So we want to work out the probability of finding T to be 5 or greater, because half of these trays, half of 10, is 5. What's the chance of having 5 or more of these trays with lots of germinating seeds? That'll be 1 subtract the probability of having 4 or fewer trays with 15 or more germinating seeds. So now we just alter our calculation here. So we go menu, 7, back to binomial CD, only now we're talking about number of trays. So there's 10 trays in total. First of all, we need to calculate the chance of having 4 or fewer trays where 15 or more germinate. So we put X as 4, and the probability of just one tray having 15 or more germinating seeds is this 0.299 number. This is why we didn't round, because this isn't yet the final answer. So the probability was 0.299127. So it's good if we use this more accurate version here. So I'm going to input 0.299127, press equals, and then equals again, and we get here a proportion of approximately 0.8512. That's not the final answer though. That's what we're subtracting away from 1. So 0.8512 and so on. So if we just calculate this finally, menu 1, again this answer will be stored as such. 1 minus our stored answer gives us 0.14877. So at this stage now, we can call this to either 4 or 5 decimal places. I wouldn't go to 3, at least 4 I'd say. 0.14877 I'm going to call it. And that's the answer for B. So B was quite a meaty question part in itself. So that's B, and above, of course, that was A. So let's now have a look at question C. So for C, we need to write down two conditions under which the normal distribution can well be used to approximate the binomial distribution. So this is just a memory test, essentially, to regurgitate in the exam. So the two things we need are as follows. We require, for this to hold, n to be large, the total number of items to be large, typically at 50 or more, the more the better, and the proportion of success, or whatever we're testing, is close to 0.5. So that's what we need to write down for C, these two facts we need. So now to set up the question for D, we're now told that a random sample of 240 seeds was planted and 140 of them germinated. So again, assuming that the company's claim is correct, we're going to use the normal approximation here to find the probability that at least 150 of these pea seeds germinate. So here we can use the normal approximation because n is large, 240 seeds is more than 50, and the proportion of germinating seeds is 55%, which isn't too far off 50%. So we can use that quite confidently. 55% is close to 0.5, n is large, so we can confidently use this approximation. But the question's saying to do that anyway. I'm just explaining why the question is correct in saying we can do this. So we're talking about, again, two things here. There's the actual distribution, which will be binomial, but because large numbers can make the calculator explode, essentially, the normal is used instead. So there's the normal approximation to the actual binomial. So I'm going to just introduce this as two different letters. X is the exact binomial, and Y is the normal approximation. So if I just call X the distribution of germinating seeds out of 240, the actual exact distribution would be binomial, and we're going to let big Y be the normal approximation to the binomial distribution of germinating seeds out of 40, then what we could say here is as follows. So from here, we can say if X is exactly binomial, 240 seeds, probability of one germinating being 0.55. My mistake, I apologise, that should be 0.55, not just 0.5. Whoops. Then Y, the normal approximation, will be normal with these parameters here, which we can fill in. So Y will be normal. This parameter, which should be the expected mean, number of seeds multiplied by the proportion of seeds which we'd expect to germinate. So 240 multiplied by 0.55. Let's do that now. That gives 132. And then what we're going to have here is a square root of n times p times 1 minus p, which is going to be 240 times 0.55 times 0.45, and all of that square rooted. So the square root of 240 times 0.55 times, if you want to do it in brackets you can, 1 minus 0.55, which, like I said, would give you 0.45. But if you're more confident doing it like this and not working anything out, that's fine. Press equals, and then we get 7.707, approximately anyway. So that's the normal approximation to the standard deviation of the actual real original distribution. So that number again was 7.707. So in 7.707, this tells us the standard deviation. So approximately 7.707 squared is the variance. Remember, the parameter for normal is the mean and then the variance. So I need to write 7.707 squared. So the standard deviation is approximately 7.707. So using this normal approximation, we want to work out the probability that at least 150 pea seeds germinated, which apparently they did. So if we now imagine this distribution here, so approximated by a normal, the mean is 132. So if I just write here that this is the normal approximation, this here is y, which is normally approximated 132, 7.707 squared for the variance. So now we need to remember to use the continuity correction here, okay? So the normal is for continuous data, so we can't actually work out on 150. The lower bound here would actually be 149.5. So at least 150 translates to the continuity correction of at least 149.5. And at least means we're looking at the right-hand side of a curve, so we're wanting this proportion here. So we're wanting the bit of a curve, the probability of it being at least 149.5. So that's going to be 1 minus the probability that y is 149.5 or less. We could do it that way, or what we could do, in fact, is just use the calculator directly. So I'll show you how to do this. So this value here is, of course, the standard deviation. This isn't the variance. This is 7.707. This is the standard deviation for the normal. So we go menu 7. We can go to normal CD. The standard deviation is the answer we just got, that 7.707 number, which we just put the answer in like so. Whoops, I put it in for mean, that's a mistake. So the mean for this normal approximation is 132. So I type 132 for the mean. The lower bound, because I want at least 149.5, the lower bound is 149.5. And because I want everything from this point onwards up to infinity, I just put a really, really large number for upper, at least 5 standard deviations away. I was going to put it as a million. That should pretty much cover everything. Well, 1 off a million anyway. So press equals, and equals again, and we get 0.01158. So we're talking almost a 12% chance, so a pretty slim chance of that actually happening in real life. So that was a lot of seeds that germinated compared to what this company's claiming. 55% of these 240 seeds would be 132. 150 or higher is actually quite a way away from the mean, so that seems relatively rare, which leads us to part E. Part E is asking us to use the answer to part D, this about 12% number, to comment on whether or not the proportion of the company's pea seeds that do germinate is different from the claim of 55%. Well, here, because that's quite rare, this may well indicate that the company is incorrect in their claim. So we just need to put that with relevance to this proportion being quite low. This is relatively unexpected, although obviously not heard of. So something along these lines would pick up the marks. So we could say, because 0.0116, this rounded to 3 significant figures, because this is a small probability, so it does seem likely that the company's claim is incorrect. In other words, the proportion is likely to be higher than 55%, if anything. So, if anything, it's that the company has underestimated how many of their seeds germinate. And I've spotted another annoying little niggle. That should say that. But apologies there. A bit of an off day for my proofreading. So, that's all from me. 2 worked exam-style examples. Now you need to try some of these yourselves, and these do take quite a bit to get your head into. This is quite hard going, I think, anyway. I'm not a natural statistician. Maybe you are, and if so, good for you. So here's my suggested exercises for you to try. Page 55, yep, pretty much the whole thing. All of exercise 3F. You can't do enough of these, really, unless you're a complete natural, which very few people are. Try all these, check the answers at the back of the book regularly. It's a good book, as I keep saying, If you're not sure, please do leave a comment on the comment section or try and search me out. I'll try and help you through as best I can. Once again, sincerely thank you for tuning in and listening. Please do like the video and subscribe, and I hope to hear from you all soon. So thank you once again, take care and have a lovely day. So goodbye from now, and see you soon.